Today we are going to know about heat transfer, the convection and the radiation types. So can you just tell me like what this body is actually looking like? Yes, yes. So basically this top, I mean these top which I'm highlighting right now, this top is actually what you are calling fins. So there's a like this is part of this body. Like fins are part of this body. Can you tell me more about this? Like what we call this entire body? Like definitely you don't call fins to this face. This face is not a fin. So the above top of these are all fins and all. So any guesses? Okay, so have you guys heard of heat sinks in like thermal transfer or this thing? Yeah. So basically, these are known as heat sinks, and these fins are actually part of that. They are like so. There are 10 fins over on the top. So so this is basically used in your PC or microchips, like even in your engines. These fins are there. So basically the material is aluminum alloy. So what we are going to do today is like through convection. Okay, through convection we are going to see like how these fins are efficiently working and what like how much heat do they transfer. Okay. So basically what is there? So the source is actually mounted on the top. Source as in the heat source, and the heat transfer is through these fins. Okay. So because why fins? Because this increases your surface area. So surface area increases for your heat transfer. So first and foremost, we have to save this as a file which is acceptable in Ansys. Okay. So you can see over here, like I'm since I'm creating this part in SolidWorks. So this the default save type is SolidWorks part file. If you are using CATIA, then the default is CATIA part, but we have to choose one Ansys importable file. Okay. So either you can choose step, you can choose IGS file also, or you can choose Parasolid. So Parasolid, why? Because Parasolid is like you can say like just like in your PNG is created as the most good quality pictures images instead of JPG format. So it's just like that. Like you can choose Parasolid over step file or IGS file. But if you are not getting any option, just like in CATIA or Creo, if you are not getting any option of Parasolid file, you can choose step or IGS file as well. Okay. So let me just rename it as heat sink, and I'm saving it on my desktop. So this is there. Okay. So when you open the Ansys, this is you kind of a welcome screen. Okay. So for CAD, I have used SolidWorks, and for analysis on that particular body, I'm using Ansys. So this is your Ansys welcome. Okay, like welcome screen. So over on the left hand side, you can see all these analysis like which you can do in Ansys. Okay, so there are like static structural analysis, steady state thermal analysis. Okay, transient thermal analysis. So we have over here is like we want to do the thermal analysis. So we are going with steady state thermal, and I'll just drag and drop it over here. So this is my project screen. This white screen is my project screen, and on the left I can choose how many, like what all lenses I can do on the single part. So if you can see over here, the engineering data is green tick and rest of all these are question mark, which means it has to be given some value. So for geometry, like if we want to import our geometry, what you have to do, you have to right click and go to import geometry. Okay. So right click on the geometry and go to import geometry, and then you have to browse your file. So this is my heatsink file over here, and I'll just open it. Now you can see that engineering data is green tick and geometry is also green tick. Okay. Now we come to setup, double click on it. And if you see on your bottom left hand side, it is over here, it is showing starting mechanical. So this is your progress bar actually, just like you having in your system also, like when you copy the file, you see a like small green progress bar. So this is basically just like that. On your bottom left hand side, whatever is happening, like you can see that this is blank. On your bottom left hand side, you can see like it is overall progressing. So yeah, now you can see that our object is imported. Okay. Now this is actually a second screen. My first screen is my project screen, this one. And if you can see over here, this is my second screen. Okay, so this is my second screen. And on your left hand side, you have all these options like geometry, material, coordinate system, etc. So let's go one by one, like what all these systems are. So first of all, geometry. If you open it, you can see this is a part. If you have two bodies, then it will be part one, part two, like that. Okay. Right now I'm having just as a part over here. Material by default is structural steel. You can see the properties of structural steel like tensile strength, Young's modulus, Poisson's ratio, everything. On this engineering data, you can see that. So if now again, like these heat sinks are not made up of structural steel, these are actually made up of aluminum alloy. So how to convert this material like from structural steel to aluminum alloy? So what you have to do, you have to select the part, and on the bottom side you can see assignment. So assignment right now is structural steel. If you click on this little arrow in front, then you can see like you can type anything like aluminum alloy. So aluminum alloy I'm taking. Now the assignment over here is aluminum alloy. So this material is actually aluminum alloy now. Okay. Coming to mesh. So this is kind of a like you can say like this is a thing which everyone asks, like why we do meshing. Okay. So consider a line. Okay. You might have studied that a line consists of infinite points in between. Okay. There are infinite points on a line. So if you say that I am selecting this edge over here, this one, green one. So this is actually having infinite points. Okay. This is having infinite points. Like this line is made up of infinite points. You cannot count the points on a particular line. So does your system. Okay, system as in this analysis software. So basically what meshing do is meshing is converting those infinite points into finite points. Okay, that's why you call it as finite element analysis, FEE. Okay, so basically if you see like every mathematical problem in the world, so it's basically a partial differential equation. So what partial differential equation is now? Like say suppose when you were in class 10th or 12th, you might have studied that we can write acceleration as dv by dt. So this is first order. So if you are going to second order, then you can write like d square x by dt square. So this is a partial differential equation. Okay, and every equation in the, I mean every equation which is like mathematical, which is actually solving a problem, is a differential equation. So what we have to do is we are breaking these infinite elements into finite elements. So it becomes a FEA. So meshing exactly does that. Okay. Now we have mesh and we have element size. So you can see like element size is default. So if you go to mesh and update, it will generate a default mesh. So this is a default mesh. Okay. But if you can see over here, like uh, it's a kind of a abrupt mesh over here like this. Okay. The point over here is like we have to fit a mesh on this object, on this body, which is suitable for it. So by default, it is the element size is default, but we can change. So like say suppose I'm going with 10. So it is 10 mm mesh now. I'll again click on update. So this is 10 mm mesh. Now if I go to 5, update. So now you can see this is a 5 mm mesh. Okay. Now one thing which is worth rememberable is your element size is inversely proportional to your processing time. Okay. Now, what is the processing time? Say, suppose, like what all steps I'm doing here, like geometry, material, mesh, these are pre-processing steps. I have not click on solve yet. Like the model is not solved yet. These are all pre-processing steps. Okay. So what thing is there? Like while it is doing all the calculation part is actually known as your processing step. Okay. So processing step takes time, and that time is inversely proportional to your element size. So say suppose my element size is 100 mm. Okay. So if my element size is 100 mm, that means if you see over here, you can see nodes and elements written over here. So with my 5 mm mesh, the nodes are 53 like this much 53,000, and my elements are 10,000. Okay. So let me just give you a brief of what a element and a node is. Okay. So anyone knows what a element and a node is? Okay. Let me just open a very preliminary like basic, which is paint. So I'll just open that and I'll show you what exactly I mean by that. So if I'm having one point, so let's suppose this is a point. This is my node. Okay. This point is my node. If I'm having 2 points at some distance, if I'm having 2 points, these are now two nodes. And if there is a line joining both of them, then this is called as an element. Okay. So element like uh, two nodes, basically connecting two nodes is what we call as an element. Now say suppose if I'm having three nodes like this, and there is a line connecting like this. Okay. So this is basically three node and three elements. This is a triangle. So before going into mesh, we first see like what all is there and what all not. So before going into that, so I'll just show you. So this is a triangle. Basically, there are two types of shapes which is being used in Ansys. Okay, so first one is your triangle, second one is your hexagon. Okay, so triangle is basically like if you can see over here, like this is one node, this is second node, and this is third node. So 3 nodes, 3 elements. Right over here, if you can see 6 nodes, 6 elements. But hexagon is actually hybrid. Hybrid as in, like, say, suppose if I'm distributing this as this, then this as this, and again, like something maybe like this. So you can see like it's forming a triangle on every side. So it's actually forming a triangle. So basically you can say that hexagon is a combination of triangles. You can say like that. Okay. Now, what if we go to 3D space? So if we are going into 3D space, then this triangle becomes something like this. If we are talking about 3D, then this triangle something becomes something like this, which we actually call a pyramid, right? In language, like in terms of what you can say as a 3D shape, this terminology becomes your. Can you see like this becomes your tetrahedron? So this shape, then it is like specifically called as a tetrahedron. Okay. So this is a tetrahedron. Again, and if we talk about 3D space, then hexagon is known as a hexahedron. Okay. So if we are talking about this, like it's a hexahedron, if we are talking about a 2D shape, like 2D shape as in this black one is the triangle and this is hexagon. If we are going into 3D, then this triangle becomes pyramid, which we call as tetrahedron, and this hexagon becomes a hexahedron. Okay. So let's come back to our Ansys. So now you can see like different nodes and elements are there. Now, say suppose I want to convert it into hexahedron. How to do that? So for that you have to go to insert and you have to choose method. Okay, right click on insert, go to right click on mesh, go to insert and choose method. Now it is asking me a geometry. So geometry is basically my this body. I'll apply. Now you can see the method is automatic. So this is actually by default. So if I go to tetrahedrons, so tetrahedrons are basically my pyramidal shapes. So if I select tetrahedron and I update, now you can see the entire geometry is in tetrahedron. I mean in pyramidal shapes, right? So this is my tetrahedron mesh. This is how it will look like. So this is my tetrahedron. Now say suppose I again want to change my method and I want a finite, a very smooth looking mesh. So smooth looking mesh is over here. Like this is Cartesian mesh. This is actually pretty smooth. I'll just show you. I'll update again. Yes, so it is done. So if you can see this mesh, see this how smooth this is. I mean, it's just like bunch of you can say like cubes arranged together as a like just like you have your Rubik's cube. So you can see like bunch of cubes are arranged together to form this beautiful mesh. So this mesh is you can say like it is smooth. Now how to check which mesh to go with? Okay, and how to define what element size you want to go with. Okay, so say suppose like this is right now I'm having only one part. Okay, I'm only having one part. So if that part is not big enough, you can go with the least possible size of element size, or you can say like element mesh, because that won't affect your system that much. Okay, system as in your PC. So I'll show you like what I mean by that also. So that is one element size. Again, like if you are having an assembly, so say suppose if you are having a car assembly. So in car assembly, you are having your wheels, your steering, your brakes, your car body, your like seats, everything. So if you are having a car body and if you are then giving like 5 mm of mesh, then your processing time will increase rapidly. Okay. Your processing time will be somewhat around 200, 300 hours, like if you are solving that. Okay. Again, if there is a small mesh size, your processing time will increase. If you are having a large mesh size, then your processing time will decrease, but your accuracy will also decrease. Okay. I mean, if you are having small element size, so this is 5 mm over here. If you are having small element size, my accuracy for the result of this, like the result of the heat transfer, my accuracy over here will be much more as compared to that I'm having when I'm like having a big element size. Using these nodes. So if I zoom in a little bit, so this is one node over here. And similarly, this is second node and there is one element joining both of them. Okay. So what happens is during the differential equation calculation, this software is like having a node over here. This node is there. So this node is actually having some coordinate point as uh, in some like X direction, it is having some value, in Y direction, it is having some value, and in Z direction, this is a point in space which is having some coordinating value. Okay. Now the thing is, the calculation happens at the node. Okay, so say suppose right now my mesh size is 5 mm. So this 5 mm is like this much far away. So if my mesh size is 10 mm, I'll update again. So this is being updated right now. Like I have been looking for this particular edge. So right now my element size is 10 mm. And if you can see that the nodes are bit separated. I mean, there's a 10 mm gap over here. You can say like that. It's bit separated over here. The more closer I go, the more precise the nodes will be, or the more closer the nodes will be. So my calculation for that, like heat transfer or static structural, anything, any calculation will be more precise. So this is the Cartesian mesh. Okay, and now let's go to the processing step. Like these are all pre-processing steps. Processing steps comes like what you actually want to apply on this particular body. Okay. Okay. So some people are asking like, what is a global and local mesh? So I'll show you. Like in the next radiation example, I'll show you. Actually, this is having a single body. In radiation, you require two body at least. So this is a convection, through convection, this will solve. In radiation, I'll show you that. So let's go to quickly to the steps. So you have two things over here which is need to be added. One is your convection and other one is your heat flux. Okay. So what heat flux is? Heat flux is basically just like your pressure. Okay. So pressure, what did it means? Pressure means force upon area, right? And what heat flux is? It's basically your heat transfer per unit area. So that is your heat flux. So if suppose you are coming to like it is asking me to select a geometry. So I'll pick this surface over here as my heat flux area. And you can see the direction is downwards, which is has to be because my source is placed on the top, and the heat transfer is happening from this source downwards towards the fins. Okay. So let's say suppose my magnitude over here is 1000. Let's say suppose like that. Convection over here, convection actually happens on the full body. So I'm selecting the entire body. It is asking me film coefficient. Film coefficient is basically like this. You seeing this fins. It's not fin coefficient, it's film coefficient. Film coefficient is different for different, like just like you are having a piece of wood. So piece like wood, the top surface of the wood is your film. So basically you can say like it's a transparent film. So you might have seen wrapping also. So wrapping is also type of a film. Okay. So you wrap your bikes, your cars, you apply your paint protection film also there. So the coefficient of the film is what we are talking here. So that is like film coefficient. Let me put again like 100. And this is ambient temperature. Ambient temperature, it means the surrounding temperature. So right now it's 22 degrees Celsius. Like we can go with 28, which is like your room temperature. So this is 28 now. And what we are looking for is deformation. So basically steady state, you can apply the values like whatever, has to happen on this particular object, and in solution you apply what you want to see. So what I want to see is a temperature. Again, click on solution. I want to see the total heat flux, and I want to see, like, say suppose yeah, only these things actually, temperature and total heat flux. So if I click on solve, so on the bottom left, you can see that it is solving, like running, building mathematical model, then preparing the mathematical model, solving the mathematical model. So it is happening. And once it is done, you can see like all are green tick. So there is green tick on every single information. So you can see now the temperature is this and the total heat flux is this. So if I play the animation, so you can see that heat flux is how the heat flux is, going. But this heat flux size, I mean, heat flux, you can say the quantity of heat flux is very less. So what I have to do, like per meter square, I'm putting it as say suppose 1000 watt per meter square. This is my heat flux. If I solve again, like I have increased the heat flux size over here, like the magnitude of heat flux I have increased. I'm solving. So this is total heat flux. This is a temperature distribution on the top. So it is like that. So this is there, and I have changed few values as in the convection. So before that it was like some 30. I'll put 30 watt per meter square degree Celsius, the film coefficient. Heat flux is 1000 watt per meter square. Now solve. Yeah, now you can see it better. So this is my total heat flux. If you play the animation, you can see like how the heat transfer is happening, like from the source to the fins. It is happening like that. This is temperature, like how the temperature are increasing. So if you can see over here, this is evenly distributed. Like these are like red part is spherical. Again, the orange part is spherical, then the green part is spherical as well, and finally the blue part. Okay. So what it is telling me, so just like you drop a stone in water or lake, right? You're seeing waves. So those are like concentric waves. Okay. So if this animation is having concentric waves, so these are my concentric waves. Okay. So which means my heat sink is efficient. You can see like the waves traveling like this. Now say suppose this is my total heat flux. This is my total heat flux like going downwards. If you want to see the arrow or the direction of heat flux, like how they are going, so you can go to edges. Like you are actually changing like how it is going, like it is showing elements. You can go to smooth contours like that, solid fill. So this is actually, I'm just, playing with the display over here. If you click on vectors, you can see like how the heat flux is traveling. So heat flux is traveling from the top. You can follow this arrow. It is traveling from the top. It is going downwards and downwards to the fins. And from the fins, you can see some diagonal arrows as well. Like this is going outwards. So these all are going outwards, 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 outwards till the face. So from the face, it is the arrows are going downwards, and then it is going like this. So if you play this, you can see like how the heat flux is traveling. So it is traveling downwards, and it is like a little bit converging over here. Some arrows are going outward. If you can see this one, these arrows are going outwards. So this is how my heat transfer is being happening. Okay, you can see some arrows over here as well. So from the edges, it is going outwards, outwards, outwards. Then some is happening like this. So this is how my heat flux is being like it's traveling. Okay, and if you can see over here, it is kind of, you can say, like converging over here, because you can see like this is the portion which is getting the maximum, I mean maximum concentration. You can see it is unit is watt per meter square over here. So the unit is watt per meter square, and this is 2330 watt per meter square. Okay, so this is 2330, and it is a concentrated heat flux over here, because the arrows, these arrows are merging into each other. So this is basically, it's having a concentration of heat flux. If I see for the temperature, so the temperature, because this top surface is by force, I mean it's my source for the temperature. Like this is the source for my temperature. So the temperature has to increase over there. So this is how the temperature is increasing. If you can see, this is how the temperature is increasing. So like for the boundary which you are asking, there is actually the boundary condition which is required over here is, I'll just show you. So you see this ambient temperature, this is 28 degrees Celsius right now. The film coefficient is actually a boundary condition only. Okay. So film coefficient is the upper top layer of this entire body is known as your film. Coming to your heat flux, we have this like on the top surface, we have the heat flux going. So heat flux is basically just like a pressure. So pressure is applying over here is, say suppose downwards. Your heat flux is also applying downwards, and the total heat flux which you are seeing over here with the vector values are this. Okay. So this is how your heat is traveling inside this fins, and you can say that yes, it is efficient because it is forming a radial loop. Radial loop, as in you can say the temperature is distributed evenly over here. So I'm getting a kind of a you can say that even surface over here like this, just like concentric waves you are having in your water while when you drop a stone in the water, you have concentric waves flowing out. So my temperature is also flowing out like that. And so you can say that this heat fins are efficient. How you can make it more efficient is you can increase this fin size. Fin size as in you can increase their lengths. Okay. If you increase the length, you can say that it is going like even achieving more surface area. So that's how you distribute it even more. Okay. So this is the training, you can say like for convection. Okay. Convection means you are transferring the heat through air particles, like through the part of the air particles. So basically this is convection, like you have this thing over here. So basically the air particles is what because finally the fins, the heat transfer from the fins are meeting into air, right? So this is how it is being traveling. So we have seen that. Now we will see an example for radiation, and in radiation itself, I'll show you how, like what a global and local mesh is. Okay. Coming back to SolidWorks, I'll quickly like draw two bodies actually in which I have to do the analysis. So I'll just quickly draw two bodies. I'll give some dimension to them. So let's say suppose 200 mm, and this is 50 mm. This is the same 50, and this is 200 mm. So I've given them a little bit of dimension over there, and I'm creating, actually I'm joining two lines like from the center. So my geometry will remain in the center, just like this. And this point to this point is coincident. So yeah, so my axis is kind of at the center. This like, it's up to you if you want to do this step or not. And I'm extruding these two. I'm extruding these two, say suppose 150 mm. So, or maybe like 300 mm, something like this. I've extruded that. So these are my two bodies. These are my two bodies. Now we have to do radiation. So radiation actually happens between two bodies. So convection also happens between two bodies, but the only point is we have the air particles. We don't have air particles in between because this is happening through gamma waves. So gamma rays actually. So this is happening through gamma rays, and we don't have any just like air molecules or air particles between the radiation and the process of radiation actually. I'll just quickly save this. So I'm actually saving this as a radiation test. Save. Now I'm opening. Like, let me just close this. This is my first part. And this is my project pane. So we have did a steady state thermal for the convection. But for radiation, we have to go with transient thermal. So transient thermal is like your dynamic thermal, like because the heat has to transfer between these two bodies, like it has to transfer. So it cannot be happening with this and this is my geometry radiation test. So my geometry is done. It's time for the setup. I'll quickly open that. So yeah, it is open now. And over here, like again, these part one and part two is there. Okay. So now we are having two bodies over here. Now someone was asking like, what is a global and local mesh? So global mesh, what global mesh is, say suppose if I'm changing the element size, like just from here, like I have selected mesh and I'm changing those element size 0.01, which is like 10 mm. So update. Now you can see that these both objects are of the same mesh size. Okay. Now say suppose if you want to change the mesh size of one particular body. So how to do that? Right click on mesh, insert and go to sizing. So these are sizing and I'll select the body. So this is the body. And over here, if you want to give a less 0.005 mm, sorry, 5 meters. So I can give the element size like that and I update that. So it is being updated. Now, if you can see the difference over here. So my part two, this is my part two, which is green highlighted. It's having 10 mm of mesh. My part one, which is this green highlighted, is having 5 mm of mesh. Okay. So global setting means like if I change the element size of this, I mean the upper part, if I change the size of this, then it will change the element size of both the objects. Okay. But if I did the body sizing for one particular body, then this body remains constant. Even if I change the size of the global mesh, like say suppose I'm doing it 20 mm. So from 10 mm I'm doing it 20. Now the one thing you will see that my part two, which is this one. So this body 5 mm mesh is still there. Okay. But this mesh is changed now. You can see the difference. This mesh is like the body with the gray. The mesh is changed, but my brown body mesh is still the same because I have given their body sizing. So body sizing won't be affected. The mesh over here is 20 mm. So I can again go to like 10 mm, update. Now it's a 10 mm mesh, okay, and the brown body is having a 5 mm mesh. Now for the transient thermal, what you have to do, right click, insert, go to radiation, okay, and it is asking me for the radiation, like the body which is being selected over here. So what I do is I'm selecting the inner body for radiation. Okay. So inner body is being selected for radiation and it is correlation to ambient, but I want a surface to surface contact. So correlation means like if something is emitted from this surface, like something is emitted, that will go straightly into your ambient, I mean in your surroundings, in your environment. But I want a surface to surface, which means from this surface to this surface. Like from the blue surface to green surface, I want the radiation to happen. So I am putting over here the from ambient to surface contact. This is emissivity value. So you might have known that for a black body, the emissivity value is 1, and for a white body, the emissivity value is 0. And the region between 0 and 1. Okay, this is where your I mean the profile values lies. Okay, like this is where emissivity is basically a ratio with respect to your black body. You know uh, how much radiation it is absorbing. So let me just give a random value, like say suppose 0.8, and ambient temperature is again like 22 degrees Celsius, which is fine. What I want to change over here. So this part 1 and part 2 both are my structural steel material is applied. So let me just change one of the body material. So say suppose part 1 is structural steel, and this part 2 from structural steel I am changing it to say suppose aluminum. Okay. Now if you can see, this is my part 1. The assignment over here is structural steel. This is my part 2, and the assignment over here is aluminum alloy. So one body is structural steel and the other one is aluminum alloy. Now the radiation is being given to this surface with the emissivity value of 0.8, and it is a surface to surface contact. I have to give over here as well the radiation value. So right click, insert, go to radiation again and select this face, apply. Again, this has to be a surface to surface, like from ambient to surface. Now we have emissivity value. For this body, for this face, I have given a emissivity value of 0.8. You can do it the same over here, but just to give a little bit of difference, I am going with 0.4. Okay. Also, the one thing which is required, so my radiations are done, like my radiation will happen from this gray to blue, like my this is how my radiation is happening from green to blue, but my radiation won't take effect unless I'm having a heat source. Okay, so for heat source, what I'll do, I'll go to insert. Now over here I'm inserting temperature. So temperature of this outer body, like say suppose I am giving 1000. So this is hotter. This is hotter side. So I'm giving like 1000 degrees Celsius. Also, I'm giving temperature on the other end as well over here from 1000, say suppose 30 degrees Celsius. So now you can see that there is a huge difference. I'll show you like what all steps have been done. So this C over here, this C side, you can say like this red zone over here is having 1000 degrees Celsius. This red zone on the other body is having 30 degrees Celsius, and between those two bodies, this blue and blue one is having my radiation surfaces. These are my radiation surfaces. So my radiation will happen from this blue area to this blue area. Okay, and since there is a like temperature difference, like a very much of a temperature difference, so that's why my radiation will happen. So let's see. I'm inserting first of all temperature. Then I'm inserting a probe for radiation. Not for reaction actually, for radiation. It is asking me for boundary. So I'll select this boundary over here. Radiation, just a second. Yeah, radiation 1. So I'll select it radiation 1, like this surface over here. And again, I am going with insert probe radiation, and I'm selecting over here is radiation 2. So radiation 2, if you notice, this is by this surface. So I have inserted the probes. Also, what I'm inserting is temperature. So geometry selection is this one, right click. So this surface temperature I want, or not this one actually. This surface temperature I want to know, like the inner one. So this temperature probe is there. Now again, I'm inserting a probe for temperature on this surface where my radiation is happening. Now, as a summary, like I'll show you the steps which is being done. So first of all, part 1 is my structural steel and this part 2 is my aluminum. Okay. Radiation is happening from this surface to this surface. The emissivity value of this surface is 0.8 and the emissivity value of this surface is 0.4. Temperature of the other body, I mean of this surface is 1000 degrees Celsius and temperature of this body is 30 degrees Celsius. So there is a huge temperature difference as well. So on the solution side, what I've did, I have attached the probes. Probes means just like you having your thermometer. So thermometer, like you put in your mouth and then it gives you like your reading, like how much fever you're having or something like that. So that is one of the probe. Okay. So probe I have attached, like this is a radiation probe. It will tell me the radiation happening on this, and the second radiation probe is actually tell me the radiation happening on this end. And then I have temperature probes, because right now over here I have temperature. I know the temperature of these outer bodies, but I don't know the temperature of this one. Like after the solution, what is the temperature? So I've attached two temperature probes. The temperature probe is over here and the second temperature probe is over here. Okay. Now this is my complete setup. Okay, now what I have to do, I'll just solve. So if you can see on my like bottom left hand side, you can see it is solving, 4% is done. So temperature probe is basically just like your thermometer. So what thermometer do is thermometer, like wherever you place the top of that thermometer, it tells the temperature of that, right? So just like if you dip it in some hot water, it is telling you the temperature of that hot water. So basically, I want to know the temperature of this surface over here. Like once the radiation starts, what will be the temperature of this surface and what will be the temperature of this surface? So that's why I have put the temperature probes over there. Probes has been, it is checking the temperature of this entire surface, and same over here. So these are my temperature probes. Okay, so now my solution is done. This is my temperature, like it is how it is flowing, like 1000 to 30 degrees Celsius over here. Now let's check the radiation probe. So radiation probe over here, it is there. If you click on results, you can see minus 1.6 into 10 to the power minus 3. That is the radiation. And over here, if you can see, it is minus 9.2 into 10 to the power minus 3 watts. So over here, like what's happening also is the temperature probe on this, you can see the result. It is 22 degrees Celsius, and the temperature probe over here, it is 22.001. Okay. Let me like if you are seeing this, like, so basically my radiation is not proper over here, because my entire back portion is blue. So what to do for this? Like my temperatures are okay, but let me just change a single value, which is my emissivity value. So if I change to 0.4, which means it will transfer, it will not absorb the radiation, it will transfer the radiation. So 0.8 is actually close to 1. That means like black body, what is, it will absorb all the radiation, right? So if you are having 1 as the black body number, and if I'm having 0.8, so basically it means it is absorbing the radiation. So like what I have done over here now, I have reduced the emissivity value so that it transmit more. Okay, instead of absorbing, it transmit more. Okay, so from 0.8, that's why I have given a 0.4. Now the model is solving. Okay, so so Manoj, like if you insert the temperature from the thermal option, it will show you the temperature of the overall, overall solution. Okay. Instead, what temperature probe is doing, temperature probe is individually giving me the values. Okay, like values of the one surface and the second surface. So if you put the temperature as a common, so that actually becomes your kind of a global. So it will tell you the, okay. Now coming to the reaction probe. Now you can see, yeah. So basically what you are saying is like I'll click on right click over here and insert go to thermal and then temperature. If you can see over here, this is my temperature. I have already did that. And if you can see on the reaction probe, these are my individual temperature of the surfaces, not the entire body. So if I want to look for a temperature, like say suppose maximum and minimum. So these are my temperature probes. And if you click on this probe itself, like on the top. So if you are going to nodes, like these are my nodes. If you are going over here, so over here it is 36, over here is 59, it's increasing like this, like this, like this. And on the very end, it is 1000. So over here it is 672, over here 403. So like that, my uh, temperature is being done. So what is happening over here, like how you are going to read the results? Okay. So how you are going to read the results? So let me just show you. Over here, like on this temperature side, you seeing this radiation probe 2. Radiation probe 2 is which one? This one. Okay. My outgoing net radiation is minus 6.4. Okay. You seeing this value minus 6.4. What it means it is absorbing. Okay, absorbing means it is minus, that's why it's a minus sign over there. So if a body is absorbing radiation, that goes into minus sign. So this is minus 6.4 over here. And if a body is transmitting radiation, I mean transmitting as in it is not absorbing, it is transmitting, so that transmitted radiation goes into plus value. Okay, right now what my conditions are, so these two are my radiation, this temperature is at 1000 degrees Celsius, the other half of this I mean the other body temperature is 30 degrees Celsius. So my radiation will be happening. And if you can see on the radiation probe 2, which is this one, this surface, so this surface is absorbing the radiation from this body. Okay, so this is the value of how much it is absorbing. Absorbing, how I came to know, because it is having a minus sign instead of a positive sign. It is having a minus sign. And how much is the value? This 6.4 into 10 to the power minus 3 is the value. Okay. And this is the temperature of this particular body. So it is 22 degrees Celsius. So this is how you can like see for what you can say, like convection and radiation. So the convection basically, since air particles are already there, that's why convection can be done in steady state thermal. But when a radiation has to occur, radiation is dynamic. So radiation, like radiation analysis has to be done in transient thermal, not in steady state thermal. Okay? We have, that's why we have did this in a transient thermal. So this is there, like everything is also, which is required is from ambient to surface. So this both the radiation values you have to change from surface to surface so that it is there. Okay. And then temperature I have shown you like how to add on the both the surfaces. Then these are the solutions. And coming back to convection, like that was all for radiation. I'll again show you for the convection side. So starting right now. Yeah, this was my earlier setup. This is how heat flux is done. So if you click on the vectors, you can see those arrows, like how it is going. And if you play the animation, you can actually see like how these are flowing like this. If you don't want the vectors, you can click over here. Like, so this is how your radiation is flowing. I mean, not radiation, your heat flux is flowing, your heat transfer is happening. So heat transfer is happening downwards direction towards the fence. So this is how it is happening like that. Temperature is increasing from the top surface. So the temperature is increasing like that. If you want to change, like if you want to see the slower version of the temperature, so there is like 2 seconds of this, you can go to 4 seconds. Now play. So everything is now slow motion like this. Okay. This is my global mesh. I have not given the like sizing for this because there is only one single body in this environment. So that's why sizing is not required. I have just given a mesh over there. So these are all the things. Okay. Now what I want you to do is like try this out and try to play with the software. Play as in you can change the element size, you can change these values, you can change the emissivity value, and then see like what is the effect on radiation over here. If you are changing this emissivity value and everything. So say suppose I am changing it from 0.4 to again 0.8. Let me solve. So right now it is being solved. You can create your own parts just like I have created this.
Hello, is it audible? Hello, Soma. Are you Soma? Is it audible? You can unmute yourself.
Yeah.
Yeah.
Okay. So I guess something has happened. It just dropped. So I was here actually. What I have done is I have changed the emissivity value of this body like 0.4 and emissivity of this is 0.8. So these are my radiation probe. If you can see now, uh, over here it is 0 point like -1. Like before that it was -6. Now it is -1. Why -1 is happening? Because now if you can see, my emissivity value is 0.8. Okay, 0.8 means it is absorbing that much instead of uh, reflecting. You can say like that. So that's why there is a drop in my net outgoing radiation value, and it is happened like that. Okay, so now what I was saying that you guys can like change these values, change the ambient temperature, change the emissivity value, change the temperature of this. Like I over here it is 1,000, on the second hand it is 30 degrees Celsius. So you what you do, just change these values as well, and then see the results. Like then see the results like what is happening. And just for your example, you can go to home, like on the top you can go to home, and there is an option like which is saying report preview. Click on that, and here Ansys will give you an entire report. Okay, like what is there, like these are the curves, these are the graphs for that, and you can get the entire value for everything. So just like this, if you are seeing transient thermal solution radiation probe 2. So these are my radiation probe 2, these are my time, and what is the like radiation reading over there. So this is how you are going to see the report for what you have did. Okay. So that's all guys, like for today's session. So we learned about mesh, how to give different mesh sizing, how to give different mesh method. So we have given the tetrahedron and Cartesian mesh as well. Now we have also studied about convection and radiation. Convection always happen in your steady state thermal. Your radiation happens in your transient thermal because it's a dynamic. Then we have learned about emissivity. We have given the features to the radiation and temperature, like we have given different values to that. And according to that, these are the results over here. You can see these are the results. Okay. Now you can change your values according to you, and you can then try with the radiation and convection steps. Okay. So that's all from me for today.
Okay. Thank you so much. Thank you.